Hello, grade 12s. My name is Natasha Barton, and today I would like to welcome you to this introduction to organic chemistry. Now, grade 12s, organic chemistry is a very important part of chemistry that you are going to be studying this year. And I say so not only because it is a big part of chemistry in general, but also because it is going to form a big part of your paper 2 exam. That is the chemistry exam that you're going to be writing at the end of the year. So, grade 12s, I do suggest that you do your best to focus and master the basics from the start so that as we build along in this topic called organic chemistry, you will find it easy to grasp all of the concepts, especially those that are taught towards the end of this section. Now, what is organic chemistry? Well, on a day-to-day basis, we tend to use the term organic to refer to things like fruits and vegetables that have been grown very naturally, where we do not use things like pesticides and herbicides that have been grown or synthesized in a lab in order to grow these fruits and vegetables. But organic chemistry refers to something a bit different. We say that organic chemistry is the chemistry of carbon compounds. And these carbon compounds can actually be synthesized in a lab and still fall under organic chemistry. Now, there are many compounds in our world that contain carbon, but there are some of them that are excluded from organic chemistry. Substances like carbon dioxide, carbon monoxide, the carbonates, cyanides, and elemental carbon like diamond and graphite have been excluded from organic chemistry. But things like plastics, which one would think are very inorganic and very unnatural, does fall under organic chemistry because polymers, which make up plastics, consist of large chains of carbon. And therefore, organic chemistry does not mean exactly the same thing as the term organic that we use on an everyday basis. Now, there are some important terms and definitions that you're going to have to understand very well and know off by heart this year, including the functional group and homologous series. We say that the functional group is a bond, an atom, or a group of atoms that determines the physical and chemical properties of a group of organic compounds. Just a reminder, physical properties include things like the boiling point, the melting point, or the vapor pressure of a substance, while chemical properties refers to how different compounds or substances will react with each other. On the other hand, the term homologous series refers to a series of organic compounds, in other words, a group of organic compounds that can be described by the same general formula. Or we can say it is a series of organic compounds in which one member differs from the next with a CH2 group. Members of an homologous series, so organic compounds that fall under the same homologous series, have the same functional group. So we can sort of compare this to different families which have, or a family that has the same surname. For example, my surname is Barton. And you may find that within a family, people have certain features that are common amongst them. For example, in my family, people say that we all have a similar smile. The smile would be the functional group, that thing about us that is similar, while the homologous series that we fall under would be the Bartons. It is very important that you understand these terms and definitions because there are many homologous series and functional groups that you're going to have to remember off by heart. Now, before we look at that long list of organic compounds that you need to be familiar with, I'd like to start off by familiarizing you with the different ways in which we can represent organic compounds. Number one, we can use the general formula. A general formula describes the or a homologous series. Remember, the term homologous series refers to a group of organic compounds that have something similar about them. I said the homologous series is like the surname, right? Where mine is Barton. And a homologous series contains compounds that have the same functional group. They have a feature about them that is similar. The general formula describes the homologous series. Number 2, we have molecular formula. The molecular formula indicates the type of atoms and the number of each atom in the specific molecule. You have now been using molecular formulae for a very long time. For example, when you write out chemical equations, you most often make use of molecular formulae. We have the structural formula. A structural formula shows all the atoms and all the bonds in a molecule. It is basically a two-dimensional way of representing a molecule. There is number 4, the condensed structural formula, which is a shortened version of the structural formula. And it shows all the atoms, but not all the bonds in a molecule. And lastly, we have 3D representations of molecules, such as the ball and stick model and the space filling model. The most important of these representations is the general formula, the molecular formula, the structural formula, and the condensed structural formula. We're now going to look at a beautiful summary from A. Oliphant's textbook on organic chemistry in order to put everything into context. Now, grade 12s, you're going to have to know the names of the homologous series, the general formulae, and the functional groups, how to draw them and describe them off by heart. So, as a starting point, let's look at the alkanes. The alkanes is a type of homologous series. The alkanes can be described by the general formula CnH2n plus 2. The alkanes only contain carbon and hydrogen atoms, but what is specific to them is that they only contain single bonds between all of their atoms. So that is their functional group. An example of an alkane is ethane, and as you can see, it only contains single bonds between carbon and hydrogen atoms, and its name, like the names of all alkanes, ends with ane. Then we have the alkenes. The alkenes have the general formula CnH2n. The alkenes, like the alkanes, only contain carbon and hydrogen atoms, but between at least one pair of carbon atoms is a double bond, so this is their functional group. An example of an alkene is ethene, and its structural formula looks like this. The alkenes have their names ending with -ene. The alkynes have the general formula CnH2n minus 2. They, like the alkenes and alkynes, only contain carbon and hydrogen. So all three of these homologous series fall under the group called the hydrocarbons because they only contain hydrogen and carbon atoms. The alkynes have a triple bond between at least one pair of carbon atoms, so that is their functional group. And an example of an alkyne is ethyne, whose structural formula looks like this. The names of the alkynes ends with -ine. Then there is the haloalkanes, which can also be referred to as alkyl halides. The haloalkanes are somewhat similar to the alkanes, except that they contain halogen atoms. So their general formula is CnH2n plus 1 plus X, where the X refers to fluorine, chlorine, bromine, or iodine because the haloalkanes contain halogen atoms. This is their not general formula, but functional group. An example of a haloalkane is chloroethane, and as you can see, it looks similar to ethane but contains a chlorine atom. The names of the haloalkanes ends with -ane, just like the alkanes, but you will see in the name words or parts of the name being chloro, fluoro, bromo, or iodo, which refers to the halogen atoms that they contain. Then there are the alcohols. The alcohols have the general formula CnH2n plus 1 plus OH. The OH is referred to as the hydroxyl group. The hydroxyl group is the functional group of the alcohols, and this is how we draw the functional group. An example of an alcohol is ethanol, And as you can clearly see in the structural formula is the OH or hydroxyl group. All of the alcohols have their name ending with R. Then there are the carboxylic acids, whose general formula is CnH2nO2. The carboxylic acids have their functional group always attached to the first carbon in their chain. This functional group can be referred to as a carboxyl group, and it is a carbon with a double bond O and also an OH, similar to the alcohols, but what makes it different is this double bond O. So an example of a carboxylic acid is ethanoic acid, and here's its functional group attached to the first carbon. The carboxylic acid names end with anoic acid. We then have the esters. Esters look similar to the carboxylic acids, so you're going to see the esters have the same general formula, CnH2nO2. Normally, you're going to find that some esters form functional isomers of the carboxylic acids. We're going to speak about functional isomers and structural isomers in general in videos that follow. The esters have a functional group that looks like this. It looks similar to that of the carboxylic acids, except this functional group is in between carbon atoms. So it's inside the chain between other carbon atoms. So an example of an ester is ethyl methanoate, and as you can see, the functional group is between other carbon atoms. The names of the esters ends with O8. Then we have the aldehydes, whose general formula is CnH2nO. The functional group of the aldehydes is the formal group, and it looks like this. With the aldehydes, we find that the functional group is always on the first carbon, and an example of the aldehydes is ethanol. As you can see, the functional group is on the first carbon. The names of aldehydes always end with anal. Then there are the ketones, and as you can see, the ketones have a general formula that looks the same as the aldehydes. That is because their functional groups look similar. The functional group of a ketone is referred to as the carbonyl group. But this carbonyl group, as you can see, lies between two other carbons. So it's in between, unlike with the aldehydes. And an example of a ketone is propanone, with its functional group being somewhere in the middle of its chain. The ketone names end with -one. So grade 12, there are 9 different homologous series whose general formulae, names, functional groups, etc. you need to be familiar with. Please do your best to learn these off by heart so that what follows is going to be very easy for you. So this brings us to the end of this first video, this introduction to organic chemistry. In the next video, we're going to take a look at the hydrocarbons, and we're going to see how you can test for saturation to see whether a hydrocarbon is either saturated or unsaturated.